Okay, so welcome to this next video in the playlist on group theory. In this video, what we're going to talk about is cyclic groups and cyclic subgroups. Okay, right. So in previous videos in this playlist on group theory, we have already talked about the finite cyclic groups. Okay, what I'm going to now do is I'm going to restudy the finite cyclic groups, but we're going to look at a different way of thinking about them from what I showed you in the video on finite cyclic groups. Okay, and we're going to look at a way of thinking about them that is more amenable to generalization. Okay, so what we're then going to do is we will generalize the concept of a finite cyclic group to the concept of the infinite cyclic group. Okay, so we'll see the infinite cyclic group, and then we'll have completed our discussion of cyclic groups. Okay, what we can then move on to is a discussion of cyclic subgroups. Okay, so we'll see how there are finite cyclic subgroups and there are also infinite cyclic subgroups. Finite cyclic subgroups will end up being isomorphic to finite cyclic groups, and infinite cyclic subgroups will end up being isomorphic to infinite cyclic groups. Okay, right, so we're going to therefore start off with a discussion of finite cyclic groups once again. Okay, so let's just remind ourselves of the finite cyclic groups then. So remember, the finite cyclic groups are a whole class of groups, okay, and they are denoted capital C and then lowercase n, okay, and you can create a different finite cyclic group by choosing little n. Now little n is always a natural number, so it's always a counting number, 1, 2, 3, 4, 5, etc. Okay, and you can choose which natural number you're going to use for little n, and different choices for little n will then give us a different finite cyclic group Cn. Okay, right, so let me remind you of what these finite cyclic groups Cn actually are. Okay, so remember, when thinking about finite cyclic groups, what you need to do is think about the cyclic set permutations of the set containing all natural numbers up to and including little n. So what you need to do is think about the set containing the elements 1, 2, 3, 4, all the way up to little n. Okay, so if you imagine little n could equal 7, then this would be the set containing 1, 2, 3, 4, 5, 6, and then 7. Okay? Right, so when building these finite cyclic groups, C little n, for some arbitrary little n of your choice, you firstly need to consider this set containing all natural numbers up to and including little n. Okay, and basically the way that we are going to generate the finite cyclic group Cn is we are going to look at all of the cyclic set permutations of this set of little n numbers. Okay, we're going to give every single one of those cyclic set permutations a symbol. We're going to stick all of those symbols into a set, okay, and that set is going to form our cyclic group C little n, basically. Okay, and the composition law on that set of symbols, on that group indeed, will be the composition of the cyclic set permutations that the symbols represent, basically. So if you're composing any two symbols together, what you'll just do is think about the cyclic set permutations that those symbols represent, compose those together, you'll get another cyclic set permutation, and then the answer to the two symbols composed together is then just whichever symbol represents that new cyclic set permutation that you've generated. Okay, so let's go into this in a little bit more detail by thinking up once again what the cyclic set permutations of this set of little n numbers actually are. Okay, right. So in the previous video where we studied finite cyclic groups, I told you a way of thinking about the cyclic set permutations in terms of a rotating disk. Okay, and you put the numbers 1, 2, 3, all the way up to little n around the outside of the disk, and then the cyclic set permutations are those set permutations which can be thought of as rotations of that disk, basically. Okay, right. Now what I'm going to do is show you a new way, a very much so related way, but a new way of thinking about cyclic set permutations. And the advantage of this new way is that it is more amenable for generalization in the case of the infinite cyclic groups. Okay, right. So, basically we know that set permutations are these bijective maps from this set onto itself, basically. So let's just draw the set out. So here is the set, and then I'll draw the set again below here so that I can show you one of these set permutations, basically. Now, a cyclic set permutation, then, is going to be a set permutation which is of the form move everything along by a certain amount. Okay, so, for instance, the identity map, where we send every element to itself. So 1 will go to 1, 2 will go to 2, 3 will go to 3, and little n over here will go to little n. This is indeed a cyclic set permutation, because this is the cyclic set permutation which corresponds to moving everything along by nothing, basically. Okay, you've chosen to move all of these symbols along by nothing. Okay, so we'll call this identity map I, okay, and that's the symbol we'll use for it in the cyclic group on n elements later on. Okay, so there's our first cyclic set permutation, this identity map, okay, which we've now denoted I here. Okay, right. So that's not the only cyclic set permutation, however, because now what we can think about is where we do actually move it along by a certain amount. Okay, so let's think now about the cyclic set permutation where we move every symbol in this set along by 1. Okay, so let me just draw out the set again. So here, 1, 2, 3, all the way along to little n. And then here we've got 1, 2, 3, all the way along to little n. Okay, so now let's think about the cyclic set permutation where we're going to move all of the symbols along by 1 then. Okay, so 1 will therefore go to 2, so we've moved 1 along by 1. 2 will go to 3, we've moved 2 along by 1. 3 will go on to 4, okay, and so on, all the way up until we get to little n minus 1, going on to little n, and then we've got a problem. Where does little n go? Okay, because there is no little n plus 1. Okay, so what we do is we loop back round, so we send little n here onto 1 over here. Okay, so there is an example of another cyclic set permutation, basically. Okay, we are moving everything along by 1. Okay, and we'll call this cyclic set permutation where we move all the numbers along by 1. We'll call that sigma. Okay, and I'll highlight sigma up here in turquoise. Okay, now, there's no reason to stop there then. There are more of these cyclic set permutations. We've had move along by nothing, we've had move along by 1, now let's do move along by 2. Okay, so once again I'll draw out our set. So here is 1, 2, 3, all the way up to little n. Here is 1, 2, 3, all the way up to little n. Okay. Now what I want to do is move every single element along by 2. So I'll send 1 onto 3 here. Okay, I've moved 1 along by 2 now. I'll send 2 onto 4. I've moved 2 along by 2. I'll send 3 onto 5. I've moved 3 along by 2. Then I'll send little n minus 2 onto little n. I've moved to little n minus 2 along by 2. I'll send little n minus 1 onto 1. I've now moved this along by 2. And I'll send little n along by 2. I'll send little n to 2. And I've now moved this along by 2. Okay, now I could come up with some new symbol for this cyclic set permutation. Okay, but I don't actually need to. I can express it in terms of the symbols that I've already got. Okay, and it makes a lot of sense to do so. Okay, so I can actually express this as sigma composed with sigma. So what I'll do is I'll call it sigma squared to remind me that actually it is just sigma composed with itself. Okay, now hopefully that should be intuitively obvious. Sigma is this cyclic set permutation which is of the form move everything along by 1. Okay, if we were to do that cyclic set permutation twice, then what would be the net result? We'd move everything along by 2, i.e. we'd end up with this. So if you copied this out twice and looked at the net result, you'd end up with this basically, and I hope that is intuitively obvious to you. Okay, right, so we'll colour in sigma squared in pink here. Okay, and we don't need to stop there as well. There are more cyclic set permutations. We could move everything along by 3. We could move everything along by 4. We could go all the way on, okay, so dot, dot, dot. We could go all the way down to where we've moved everything along by little n minus 1, okay? So let me just show you this. So once again, here is our set, 1, 2, 3, all the way up to little n. Here is it again. Okay, now what I'm going to do is I'm going to move it along little n minus 1. So if I move it along little n minus 1, then I can call this sigma to the power of little n minus 1. Okay, because it's going to be do sigma little n minus 1 times. Okay, and we'll have it denoted in green here. Okay, so where is everything going to go? Okay, so 1 is now going to go all the way over to little n. When you move 1 along by little n minus 1, 1 goes to n. Okay, 2, there's no little n plus 1 for it to go onto, so it's going to have to loop back round. It'll have to go to where 1 is. 3 will have to go to where 2 is. 4 will have to go to where 3 is. And then little n is going to have to go to where little n minus 1 is. Okay, right, so now we have got all of these permutations which are of the form move everything along to the right by a certain amount. Now you might be wondering, well, do we need to consider the permutations where we move everything along to the left by a certain amount? And I would say that's a very good point. However, you don't need to worry about it at all because of the way that we have cycled round, basically, when we ran out of things on this side, basically. Okay? My claim is that actually we have got all of the movements to the left in this list of set permutations that I've created. Okay, and hopefully just looking at this one you might be able to understand that. Okay, look at this. This is effectively move everything along to the left by 1. Okay, we've moved little n to n minus 1, we've moved little n minus 1 to little n minus 2, we've moved 4 onto 3, 3 onto 2, 2 onto 1, 1 had nowhere to go, so it's had to loop back to n. This is effectively move everything to the left by 1. So in fact, you can either think of this as move everything to the right by little n minus 1, or you can think of it as move everything to the left by 1. And indeed, actually, every single one of these, okay, can be thought of as either moving it along to the right or moving it along to the left. Okay, so for instance, this one here, you can think of this as moving it along to the right by 1. Okay, and indeed that was the way we thought of it. However, you can also actually move this, think of this as a movement to the left. Look at where n is going. It's going to the left. It's going to the left by little n minus 1, basically. So you could also think of this as a movement to the left by little n minus 1. Okay, and then when 1 had nowhere to go, it would have to go to where, well, it would, if we move 1 little n minus 1 to the left, it would then have to go to where 2 is, basically. Okay, and 2 would end up going to where 3 is. Okay, so I'll just try and make that a little bit clearer. When we move little n to the left by little n minus 1, it goes to where 1 is. When we move little n minus 1 to the left by little n minus 1, it'll end up going to where n is, as we've got here, and then for the rest of them it's all the same argument, basically. So basically all of these set permutations that we've viewed as moving to the right by a certain amount, you can also reinterpret them, rethink of them as movements to the left by a certain amount as well. Okay, so that's why we don't need to worry about movements to the left, basically. We have got all of the set permutations here that are of the form move to the right or move to the left by a certain amount. So we have actually got all of these cyclic set permutations which are of the form move to the right or left by a certain amount, basically. Move along by a certain amount. Okay, right. So how many of these cyclic set permutations actually are there? Well, there is only little n of them, basically, because as soon as you tell me where the element 1 goes to, I instantly know which cyclic set permutation you are talking about. If I know where 1 goes to, then I know how much you've moved 1 along, and then all I can do is then move everything else along by that certain amount, otherwise I wouldn't have a cyclic set permutation. Okay, so that means that the number of cyclic set permutations is exactly the number of different places that you can send 1 to. So how many different places are there that we can send 1 to? Well, we can send 1 to 1, we can send 1 to 2, we can send 1 to 3, and this argument goes on, we can send 1 all the way up to little n. So that means that there are little n places we can send 1 to, and all of those different places we can send little 1 to will give us a different cyclic set permutation, which is what we've got written out here. So that means that the order of one of these finite cyclic groups, c little n, is just exactly little n. Okay, right, so to create the finite cyclic group c little n, then what you're going to do is you're going to stick all of these symbols together into a set. So you're going to put the identity in, you're going to put sigma in, you're going to put sigma squared in, and you'll go all the way up to sigma to the power of n minus 1. Okay, like so. So there's our set that's going to underlie this group. Okay, now what we need is a composition law on this set of elements. Okay, so as I said earlier, the way that we define the composition on this set of elements is just by thinking of composing the cyclic set permutations that these symbols represent. So what you'll do is you'll define a composition law like so. Okay, so you'll put every element up here, so you'll give every element a column of its own, like so. Okay, and you'll give every element a row of its own, and you'll need to go through this huge great composition table and define what every element composed with every other element is actually equal to. And the way you'll do this is for an arbitrary little element little x and an arbitrary element little y, x composed with y will be the cyclic set permutation, the symbol that represents the cyclic set permutation that you get when you first do y and then do x. So what you'll do is you'll think, okay, y represents some cyclic set permutation on this set here. Okay, what happens if I first do the cyclic set permutation y and then I do the cyclic set permutation x? I will get a net new set permutation, and basically what I then do is then I just think, okay, what's the symbol that represents that new set permutation, and I stick that in as the answer in my composition table. Okay, so let's just talk through why that actually forms a group then. Okay, so we need to check firstly that it obeys the axioms of group theory. Okay, so we need to make sure that it's closed first and foremost. Okay, so what we need to check is that if we compose any two elements together, we end up with an answer that is within the group. So basically what that means is that we need to check that actually when we compose any two cyclic set permutations together, we end up with another cyclic set permutation. Okay, because if it was the case that we composed two cyclic set permutations together and then got a set permutation that was not a cyclic set permutation, then that new set permutation that we'd achieved would not be represented by a symbol in this set, and therefore the answer to the composition would be outside of this set, basically. Okay, and it wouldn't be therefore closed. Okay, well hopefully it's obvious that if you compose any two of these cyclic set permutations together, you do actually end up with another cyclic set permutation. Okay, if you compose two permutations which are of the form move everything along by a certain amount together, you end up with another permutation of the form move everything along by a certain amount. So if you say move everything along by 2 and then move everything along by 3, you still end up with a permutation that is of the form move everything along by a certain amount, basically. In this case, move everything along by 5. Okay, so hopefully you can see that when you compose two cyclic set permutations together, you cannot possibly end up with a set permutation that is not a cyclic set permutation. Okay, right, so that's closure then. Okay, associativity is the second axiom of group theory. Okay, we don't need to worry about associativity at all because of the fact that we are thinking of this composition law as representing the composition of set permutations. We know that whenever we think of the composition law as representing the composition of set permutations, then it instantly obeys associativity, because if you compose 3 set permutations together, okay, that has an answer. It doesn't matter where you put the brackets, basically. It really does not matter. It has one and only one answer. Okay, so no matter where you put the brackets in the expression of 3 things composed together, it has to give the same answer. Okay, so we know that associativity, we will get that, okay. Third axiom of group theory is that we need an identity element. Well, we have the identity set permutation represented by a symbol in our group, okay. My claim is that that symbol will now compose with any other symbol, either on the left or on the right, to give the arbitrary other symbol back again, okay, and therefore I will be an identity element in this group. Now, the reason for that is quite simple. When you compose the identity set permutation with any other set permutation, on either way, basically, either way round, you end up with the other set permutation back again. Okay, the identity set permutation doesn't affect the other set permutation that it's been composed with. Okay, so that's why we'll have an identity element. And why do we have inverses? Well, basically, what I have argued is that actually we do have all the movements to the left in here as well. Okay, we didn't have to consider permutations of the form move everything to the left by a certain amount because they were already all in this, basically. Okay, so for any cyclic set permutation that I've got here, which we are thinking of as move to the right by a certain amount, you will have another cyclic set permutation somewhere in here which will be moved to the left, well, which could be thought of as moved to the left by that same amount, and therefore those two will compose with one another either way round to give the identity set permutation back again. So the symbols representing them will compose with one another to give the identity symbol in our group here. Okay, right. Another way of thinking about that is to remember that if we end up moving everything along by n, okay, then that is the same as the identity set permutation. So let me say that again. Okay, here is our movement to the right by little n minus 1. What would happen if we considered sigma to the power of n? What would this be? Okay, well now we'd move 1 along even further, but there is nothing along even further. So we'd end up moving it back onto where 1 is. We'd move 2 along even further, so it would go 1 to the right again. So now 2 would go to where 2 is instead of going to where 1 is. 3 again would go to where 3 is, and you can see that everything would end up going to itself, basically. So sigma to the power of n is actually equal to the identity element. Okay, so what that means is that if you take any element here that's move everything along to the right by a certain amount, and you compose it with another element which is move everything along to the right by n minus that amount. So let me just write this out in symbols, it'll probably be easier. So if I've got some element, sigma to the power of a, where a is some little natural number, okay, between 1 and little n minus 1 here, okay, if I want to find you the inverse of this, then what I can consider is what is sigma to the power of n minus a, okay? If I compose those two together, what will the answer actually be? Okay, well this says move everything along to the right by little a amount. This says move everything along to the right by little n minus a, which is still some natural number, okay? What's the overall effect of that? Well, I'm going to end up moving everything to the right by n minus a plus a, okay, which will be sigma to the power of n basically. Okay, and this actually brings us on to the more general way that you compose these together. Okay, and I should have probably discussed this earlier before we went on to this. So how do you compose any two elements together in this group? If you have sigma to the power of a, and you're composing it with sigma to the power of b, where little a and little b are both elements of the natural numbers, okay, they're both between 1 and little m minus 1, then the answer is just sigma to the power of a plus b basically. Okay, you just add the powers, okay, because this means move everything along by little a, this then means move everything along by little b. Okay, what is the overall effect of doing that? Well, it's move everything along by a plus b basically. Okay, now what you can query is what if that goes over little n? Okay, what if it ends up as being higher than little n? Well, then all you need to do is factor out the sigma to the power of n basically, okay, and get that it's sigma to the power of n times sigma to the power of some leftover bit, which I'll call r, okay, and then you can acknowledge that sigma to the power of n is just the identity element here, and therefore the answer to this is just sigma to the power of r, the bit that's left over basically. Okay, so that's what you'll do if the power here goes over or is equal to n. Okay, so coming back to this argument over here, where we're talking about inverse elements, if I have some sigma to the power of a here, and I want to find its inverse element, then all I need to do is find you the bit, or the movement to the right that would compose with this to make it overall move everything to the right by little n. Okay, so the complementary portion basically that takes the power of sigma up to little n basically. Okay, so if I do have some sigma to the power of a, then I can find you this element sigma to the power of n minus a, and when I compose those together, I will now get sigma to the power of n, which I know is the identity basically. Okay, so let me give you a concrete example which I hope will make this more apparent. Okay, so if we for instance have sigma squared, okay, and we want to find its inverse element, then we could consider the element sigma to the power of n minus 2, okay, because this will move it along by what is left over, the amount that you need to move it along that is left over to take it overall to the operation of moving it along by little n basically. Okay, so that is how you can find inverse elements for any one of these elements of this group basically, by thinking about what element will compose with it to overall make the net set permutation a movement of everything along to the power of n basically, which we know, everything along by n, okay, which we know is equivalent to not moving anything at all. Okay, right, so those then are the finite cyclic groups, C little n. In the next video what we'll do is generalize this concept to the infinite cyclic group.